All right, so yesterday we talked about going from condensed formula to bond line formula. There's not really a perfect way to do this. I have students where they'll physically draw out every single hydrogen and then work backwards, eventually going from a complete structure to a bond line structure. Whatever works for you. You're welcome to use scratch paper on exams as well, so if you need scratch paper, you can use that space. All right, I'll share with you my biggest pet peeve. Meaning something that irritates me. I'm going to do this in all caps to show you how serious I am. Never draw a carbon with 5 bonds. Nothing crushes the soul of an organic chemistry teacher more than seeing this. Does anybody know what we call it in the chemistry world? Texas carbon. Because everything's bigger in Texas. So the Texas carbon is a carbon that has 5 bonds. What I do when I see it on an exam, quiz, homework, is I have an arrow to it and I draw a frowny face, and you will know that you disappointed me. So try to avoid disappointing me and avoid drawing Texas carbons. I know sometimes they slip in, but we'll do our best to avoid them. You will never run into a situation where you run into a carbon with 5 bonds. And there's always one student a year, they're like, well, I read a research article that there was a molecule that was CH5. And I'll say, yes, you're not wrong, but they did that in the gaseous phase and observed it for a fraction of a second. We're not going to count that, right? So as far as we're concerned, carbons can have 3 bonds or 4 bonds, but never ever 5 bonds. So always make sure you avoid these Texas carbons. All right, now the fun stuff, functional groups. How many of you have ever used Quizlet? So Quizlet is a really good study aid. I have a link here with all of the different functional groups. You can use this as a game. You can use it as a flashcard set, whatever you want. I'll try to put the link up on the course website too, in case you don't want to copy this down. But let's quickly talk about the different classes of functional groups. We're not going to hit all of them. There are dozens and dozens of functional groups. Instead, what I'm going to do is focus on what I think are the most important ones. So the first ones are hydrocarbon functional groups. So hydrocarbon is something containing hydrogen and carbon, right? Makes a lot of sense. So let's say we have a carbon-carbon bond. This would be referred to as an alkane. Does anybody know what we call a carbon-carbon double bond? Alkene. It's really confusing for students. Essentially, the alk prefix means that it's a hydrocarbon. The suffix will vary from ane to ene, depending on whether or not it's a hydrocarbon with a single bond or a double bond in it. So we need to be very careful with the suffixes that we use. All right, and then the last one we've got here is carbon-carbon triple bond. This would be an alkyne. So like I said, the prefix alk is used for a hydrocarbon. In this case, it's a hydrocarbon containing a triple bond, so we need to use the Y-N-E suffix. All right, there's a few more. The next ones are considered aromatic. And this actually is kind of frustrating, and I'll show you why. Right, so students will look at this and they're like, these are all pretty much the same, right? But they vary a little bit, right? All right, so let's do the top one. Does anybody know what that's called? Benzene. So that's the parent. That's the parent molecule, just 6 carbons, 6 hydrogens in this ring orientation with alternating double single bonds. We'll talk more about this later. It's a really important organic molecule. All right, the next one. Does anybody know what the squiggly line means? Just means it's attached to something. So that could be any attachment point. So it could be an oxygen atom, it could be a nitrogen atom, it could be another aromatic ring, it could be a variety of different things. It's just saying we essentially have a benzene ring hanging off of another molecule, right? All right, whenever we run into this, we call this a phenyl group.
So is that our carbon half a squiggly then too?
That's a good question. In some cases, it could be a carbon. However, we need to distinguish it from the one underneath it. Because if we look at the one underneath it, you notice how, whoops, we have this spot right here. What's that going to be? That's a carbon with two hydrogens, right? So specifically, if we have this group underneath where we've got a CH2 spacer between something else, that's typically referred to as a benzyl group. Make sense? So typically, if you just see a molecule, let's say we've got a molecule that looks like this. And I'm focusing on this portion. What would we maybe call that? Would we call it a benzyl? Probably a phenyl because it doesn't have a CH2 coming immediately off of it, right? If we look at this carbon right here, that's not a CH2, so we wouldn't want to call that a benzyl group. So try to be aware that we need to distinguish these. It's a subtle difference, but it's a difference that confuses a lot of students. So I like to introduce that early. All right, makes sense? Oftentimes what you'll see with these phenyl groups is it abbreviated as pH. That's just kind of the placeholder for that ring system. That way you don't have to draw it all out. And then down here, I believe it's BN. It's BN or BZ, I'm actually forgetting, but it's represented differently, so we do need to be aware of that. Does that make sense? So all of these contain only hydrogens and carbons, and we need to call them by different names. All right, next one are heteroatom-based functional groups. What does it mean when I say heteroatom? Non-carbon or hydrogen, right? So it's a non-carbon or hydrogen containing atom, all right? So we've got a bunch of those in chemistry. So I'm just going to make a list. First one will be Rx, where X is going to be equal to a halogen. Where are the halogens located? Group 7, so it's going to be fluorine, chlorine, bromine, iodine, all of those in that column, right? All right, what do you think the R stands for? Yeah, it's going to be anything before it. Typically, it's a carbon placeholder. However, sometimes it's hydrogen. All right, this functional group, anytime we've got a carbon atom bonded to a halogen, is referred to as an alkyl halide. If you remember, I was saying that alk stands for what? A hydrocarbon, right? So it's basically saying a hydrocarbon bonded to a halogen, right? So it could be an alkyl fluoride, it could be an alkyl chloride, alkyl bromide. There's a bunch of them, right? So we could even be more specific and indicate the type of halogen on there. Does that make sense? All right, next one. Does anybody know what this would be called? Again, R in this case is usually going to be a carbon, not a hydrogen. Otherwise, we're just drawing water. Alcohol. Important thing to remember. Some people think, oh, alcohol, that's the stuff you buy at the grocery store and can drink, right? If you're a drinker. Do we want to drink all alcohols? No. There are some alcohols that will very much kill you. So be aware, alcohol is the generic term for any hydrocarbon that has that OH group coming off of it. All right? Next one looks pretty similar. However, it has a sulfur on it. Anybody know what this is called? Thiol. All right, then next one. What would this be called? Amine. So these are really important in biology, especially these two. Thiols are found in one specific amino acid, cysteine. It's important for how proteins fold together. Amines are obviously important in amino acids as well. So this would be a primary amine, meaning that the nitrogen is bound to one carbon, right? You can also have nitrogens that are bound to two different placeholders. These are still called amines, but what do you think this one's called? Secondary, because now it's bound to two different carbon groups. You can keep on doing this, and you can have amines where you have three groups. This would be a tertiary amine. You can even have four on there, but what would that do to the nitrogen? Would it give it a charge? Yeah, I would give it a positive charge. So that would be a quaternary ammonium salt. So normally it's not called an amine anymore because now it's ionic. All right, next one. It's kind of similar. Would this be an alcohol anymore?
No.
Why not? Doesn't have an OH. So this is unique and completely different from an alcohol because the oxygen is bonded to two carbons. All right, this is called an ether. It's a pretty common functional group in organic chemistry, and it's found in some of our common lab solvents too. All right, we have the sulfur equivalent, where we have sulfur in the middle. This is called a sulfide. We'll talk more about sulfur chemistry a little later. We're not going to do a whole lot of it this year. And then one that you might see in biology, again going back to the amino acid cysteine, is two cysteine residues on amino acids can actually link together, causing a bridge between two strands of a polypeptide. This is called a disulfide, or often it's referred to as a disulfide bridge. Does that make sense? So these are just a handful of them. There are other ones as well you might run into, but these are the key ones that we really need to make sure that we remember. All right, the next ones are the carbonyl functional groups. All right, so just like before, we're going to have that placeholder as an R group, and that R group can be a hydrogen or a carbon. Usually it's a carbon, but on a handful of occasions it might represent a hydrogen. And then over here I've got this Y group. This is kind of my made up placeholder. All right, so what I'm going to do is I'm going to make a list of what if Y is some sort of atom. Okay, so let's imagine that molecule where we replace Y with a hydrogen. So we swap out the Y for a hydrogen. This would be called an aldehyde. So what I mean by that is an aldehyde would be a compound that looks kind of like that. Does that make sense? So to show this, I'm going to do that squiggly line thing again and say that just means that the hydrogen's coming off there. Does that make sense to everybody? It'll speed up the process a little. All right, so that's a simple one. Aldehydes are pretty common in organic chemistry. We'll do a fair amount of work with aldehydes. All right, the next one means that we have some sort of hydrocarbon coming off that Y position, right? So we've got a hydrocarbon coming off of each side in this case. This would be called a ketone. Students will always ask me, will you mark me down if I spell it wrong? If I can understand what you're trying to write, I will give you credit. But if you're writing like aldehyde ketone, I'll be like, no, you don't get credit for both of those. So try to have it at least somewhat correct there. All right, next one. What happens if we have an OH group coming off of there? It's not referred to as an alcohol anymore because it's coming off a CO double bond. This would be referred to as a carboxylic acid. So remember, anytime you see this, it is not an alcohol. We want to be as specific as possible when we're describing things in organic chemistry. The more accurate way of describing this whole group is to call that entire group a carboxylic acid, not an alcohol. That's more descriptive about what's going on. So make sure you're descriptive when naming things. All right, next one's a little bit different. So this one doesn't have an OH group, it has an OR group coming off of it. It's called an alkoxy group. So an alkyl group we know is a hydrocarbon. Alkoxy is a hydrocarbon with an oxygen in there. So it has an oxygen first, followed by a hydrocarbon. This is called an ester. The most common mistake students make is they flip-flop ether and ester because they sound really, really similar. So make sure that you come up with some sort of tool to remember an ester is the one that's attached to a CO double bond, not in between two carbons. All right, next one's a little bit different. This is called an anhydride. All right, so I'll give you an example of one right here. So an anhydride is when you have two carbonyl groups, meaning two CO double bonds, with an oxygen in between them. So this isn't a carboxylic acid, right? There's no OH group coming off. It's not an ester, because with an ester we said this R was going to be a hydrocarbon. It's not really a hydrocarbon that's attached, it's another carbonyl group, so we need to call this something different. So an anhydride looks like that. All right. Next one is if you have a halogen coming off. This is called an acyl or acid. Let me clean this up. Halide. These are commonly found in tear gases, things like that. They can be somewhat difficult to work with. We'll talk about the chemistry of these later on in the year. And then the next one could be some sort of amine. And I'll just make a little note under here. It could be primary, it could be secondary, it could be tertiary. It doesn't really matter. All of these are referred to as amides. Where are these found? Those of you that have taken biology. Which important biomolecule? Polypeptides. So polypeptides are actually linked together amino acids, and the linkage is actually an amide bond within them. So it's a very, very important bond in biology. Does that make sense? All right. I really try to avoid having students memorize their way through this course. The best way I describe this is it's like learning a language. We do need to memorize some of the small tidbits, but practicing a language is how you get good at it, right? So we need to make sure that we do memorize the terms, but that we practice them more importantly so we know how to use them in context. Yeah?
Could you describe the anhydride again?
Yeah, so in an anhydride right here, let's actually, I'll do it over here so we have more room. So we'll space this down here. The black portion we're going to keep as is. So it's going to look like that. But now I'll do the Y portion in green. You see how this portion is now where that Y used to be? That's an anhydride. So really you could take any of these groups over here and plug them in where that Y used to be, and you'd be making that functional group. That's a good question. Does that help? Okay, just want to make sure. Any other questions on functional groups?
So if we're plugging in another one,
Mm-hmm.
we've got the squiggly line, is that, I'm still confused on whether or not it's carbon or not, where the squiggly ends.
So where this squiggly is right here,
Yeah.
that's just the attachment point to where y used to be. So you see how this whole thing used to be this whole y portion? We're just swapping it out.
Okay, so the squiggly would technically be between the O and then the other O.
Yes, exactly.
Okay.
So we could do this with a variety of these, right? So let's think about an amide, for example. We would still have this standard carbonyl group, but now what we would do is we'd take this whole chunk and we'd throw it in to where that Y used to be. We'd say NH2, and now if we're looking at this entire group would be called an amide. Does that make more sense? I kind of condensed it down just for the sake of space for everybody.
And that would be a first degree right there.
Yes, this would be a primary. Yep. Great questions. How many of you have seen functional groups in your other courses? I'm just curious.
Just starting today.
Just starting them? All right. That's good. I know some instructors really prefer certain naming conventions. We'll stick with the organic chemistry ones. Another common thing I've seen students do is they look at this functional group and they call it a hydroxy functional group. You're kind of right, kind of not right, depending on the situation, if you call it a hydroxy group. For right now, let's stick with calling these alcohols. And then we'll talk about when you would use the term hydroxy group later. Hydroxy group is kind of the secondary priority for naming system. It's not the preferred naming system when that's the most important functional group. All right, now we get to do the fun stuff. I know that was fun, but this is more fun. All right, introduction to resonance. How many of you have heard about resonance outside of this course? A few people? All right, so I'll show you the problem with Lewis structures and we'll see why we need resonance in our lives. So Lewis structures do not always describe a molecule well. And I'll show you an example. Let's think about this anion right here. This is called the formate anion. All right, my question for you is we've got two different carbon-oxygen bonds, right? We've got this one that I'm showing with a red arrow, and then one with a blue arrow. Which one do you think is longer based on the structure as drawn here? Blue one? Why? It's a single bond. We know that single bonds tend to be longer than double bonds, right? That also is incorporated into molecular orbital theory, right? If I were to look at this oxygen right here without knowing anything about resonance, I would say, well, there's 3 lone pairs and 1 bonded atom. Electronically, this must be maybe sp3 hybridized in order to accommodate the bond to that carbon and all 3 lone pairs. Shouldn't it be tetrahedral and have an sp3 lobe? Not quite, and we'll talk about that in a second. But normally we'd say this should be the longer bond. And we would say, shouldn't this one be shorter because it's a double bond? The answer is this is completely incorrect. Instead, what happens when we observe this is something kind of unique. Instead, we have bonds to these oxygens, but it's not a double bond. It's actually in between a double and a single bond for each of these. These are actually the same length. All right, but we know that there's a negative charge. Where do you think the negative charge is going to be located? Because over here we had a negative charge. It didn't go anywhere. It has to be somewhere. Where would we describe the location of that negative charge now? What do you think?
Is it kind of like dipole of this? So it would be between 2 oxygens?
Yeah, I would say it would be shared between the 2 oxygens, absolutely. So instead of forcing that negative charge to reside on any one of those oxygens, it's actually going to be shared. How do we show that? I really like doing the delta minus symbol to say that negative charge is shared between those both of those oxygen atoms. This is a more accurate view of kind of imagining the electronic layout of this molecule. Does that make sense? All right, so now we've got to kind of go back to orbital theory too to describe this.
How about the uncovalent shape?
Yeah, that's a good question. So if we think about this central carbon right there, what do you think the hybridization is going to be for that carbon? sp2. So the geometry must be trigonal planar, and what would the bond angles be? 120. We'll talk about some kind of weird exceptions to that a little later, because there are times where it's not always what it appears to be. But for right now, we'll trust our gut.
So there's no real fourth bond on it, it's just the two half bonds?
Yeah, that's a good question. So if we think about this bond right here and this bond right here, it's not a double bond. It's not a single bond. In this case, it's a bond order of 1.5, meaning it's a bond and a half. So there are situations where we're on the in-between side of a single and a double bond.
Basically counts as four.
So between the carbon and oxygen?
All of the four bonds coming off. So you need a total of four coming off of the carbon.
Yes, so off of the carbon we have four bonds. That fourth bond is kind of shared between both CO bonds. Good questions. All right, so I'll show you an example so that we can view this using molecular orbitals. All right, so this first example has a carbon-carbon double bond, carbon-carbon single bond, and I'm going to show all of the hydrogens right now. All right, this carbon has a positive charge because it only has 3 bonds on it. All right, my question for you is what's the hybridization of that carbon? Would it be sp, sp2, or sp3? sp2, perfect. All right, what about this one? sp2. What about this one? Would it be sp2 or sp3? sp2, it has 3 bonded atoms, no lone pairs, right? So it must be trigonal planar and must also be sp2. Okay, this is called the allyl cation. And what we need to do is we need to imagine what's going on between all of these sp2 lobes. So what I'm going to do is I'm going to draw the carbon backbone. So try to follow along. Let me clean up this carbon. We're just drawing the carbon backbone with single bonds. We know the carbon on the left has 2 hydrogens bonded to it. The middle carbon also has a hydrogen. I'm going to offset it a little to the right. And then this one also has 2 carbons. And we know each of the carbons must be sp2. However, there's another orbital we're not considering. What are we not accounting for outside of the sp2 orbitals? How do we form the double bond? The p orbitals. So let's show the p orbitals. Okay, so as drawn right here, we know that there's a pi bond between those left 2 carbons. The carbon on the far right also has a p orbital, right? Is there anything in this p orbital right here? No, it's empty. It's completely empty. So what you can do is you can show that with a positive charge, but all of these are p orbitals. All right, we know that charged molecules tend to be a little less happy than neutral molecules, right? Neutral molecules, in general, are going to be more stable than charged molecules. Okay, in this case, we do have a charged molecule. We have a positive charge. Okay, that's not the greatest thing to have a charge, but what might make it more happy is to share that positive charge across multiple atoms. Can you see how the p orbitals are all in alignment though, as I have them drawn. They're all pointed straight up and down. So in this case, the electron density in that pi bond on the far left can actually kind of migrate over to the right-hand side as well. So let's kind of imagine this, and I'm going to redraw it down here. We still have these p orbitals, but this time the pi bond is going to migrate kind of over to the right-hand side and form a double bond, so to speak, between those two right carbons. All right, what else am I forgetting? My charge, right? Where do you think the positive charge must be? On the left side. So now that positive charge has essentially moved its position over to the left-hand carbon. All right, whenever we show resonance structures, we always like to show them with these brackets around them because these are essentially the same structure represented two different ways. Kind of like I was showing you on that quiz key, both answers were correct for that first problem on the quiz. And then in addition, we'd like to show that they're related by using a two-headed arrow. What does a one-headed arrow mean? A reaction. In this case, is it a reaction? No, it's just electrons kind of moving around in space. So we want to use a two-headed arrow. All right, so let's do the same thing over here. We'll do a double-headed arrow, and then we'll redraw this. Like that, and then I'll put brackets around this side as well. And we know that the positive charge must be on the left-hand carbon. All right, so kind of going back to the weird concept. Where's the positive charge? It's shared. Between which two atoms? The exterior carbon atoms, right? So it's not that the positive charge belongs to either one. It's essentially in between. It's half on one carbon, half on the other carbon. Does that make sense? Yeah.
So it's sharing between the two carbon on the left side?
Yep, so positive charge could be either on the left-hand carbon or on the right-hand carbon. It's a little confusing to think about, but it means that each carbon is sharing that positive charge. It doesn't belong to either one. It's confusing because when you take general chemistry, you're often taught this atom has this formal charge, this atom has this formal charge. When you get to organic chemistry, we're like, yeah, we were lying to you. Sometimes atoms have partial charges, meaning they don't have a true positive one. Maybe it's positive 1/2, and that other half is shared with a different atom. So you'll find that we lie to you a lot in chemistry. It's not meant to be discouraging. It's very complicated to teach this in general chemistry when you don't have a great understanding of orbitals at that point. All right, let's try one more. This one's going to get a bit more abstract. All right, so it's going to look really similar. And let me point this down more just so the bond angles look better. All right, so you see how this looks really similar to the last one? Main difference is we have a lone pair now, which has changed the formal charge of that carbon to negative, right? All right, so let's go ahead and take a look at this. What's the hybridization? sp2. What about this one? sp2. All right, most students, when they look at this one, would say what? sp3. All right, if it's sp3, what bond angles would we predict? 109.5, right? However, experimentally, we can check this using something called X-ray crystallography that allows us to see the bond angles within molecules. And what we're seeing is we're seeing bond angles that are 120 degrees. What do you think might be happening? Do you think it's sp3? No, what's the experimental data telling us? Must be sp2. Yeah, so let's take a look at what's going on. So according to experimental data, all carbons are sp2. So let's try to take the orbital picture and figure out why is this not sp3 and why is it sp2? So same idea. I'll draw the backbone over here. Okay, if they're all sp2, it's going to look a lot like that molecule above that we were working on, because we know that sp2 hybridized atoms have p orbitals that are left over, right? So all of these must be p orbitals. Okay, as I have it drawn, we know in the original Lewis structure, we have a double bond between the leftmost carbons. So we can show these as sharing electrons as a pi bond, right? All right, my question for you is, where do you think these lone pairs are? They must be in the p orbital, right? Because experimentally, we know that's the only spot they could be according to the geometry. Okay, so I'm going to go ahead and draw those in there, and I'm going to say, all right, that must have a negative charge, meaning a pair of electrons in that p orbital. All right, so now we need to figure out, okay, why is it beneficial to have those electrons in a p orbital versus an sp3 lobe, which is what we originally predicted? What do you think? Yeah, we can move that negative charge just like we moved the positive charge as long as it's in a p orbital, right? So can you see how all of those p orbitals are in alignment? That negative charge can migrate because all of those p orbitals are in alignment. If it were an sp3 lobe, what's the problem? Yeah, so we'd have one p orbital sticking straight up and down in that middle carbon. An sp3 lobe wouldn't be in alignment, though. It'd be kind of sticking out in a way. That wouldn't let the lone pair delocalize as easily. So if it's in a p orbital, that's actually better. Okay? So we can draw this kind of like we did before. We haven't changed the p orbitals. They're still there. Let me move this hydrogen over for clarity's sake. But now the pi bond would be between the two right-hand atoms, and then the lone pair could migrate all the way over to the right-hand side. So these would be a pair of resonance structures. All right? It's a little bit tricky and confusing, right? I know this gets very abstract, so what we're going to do is we're going to spend, whoops, that's not a pi, this should be a negative. We're going to spend the next 2 days just practicing resonance, because this historically is one of the biggest conceptual hurdles for organic chemistry students. So make sure for this chapter that you do as many resonance problems as possible. How many of you read through the student advice from last year? A few people did. That's okay. If you read through there, my students had a joke last year that whenever they didn't know the answer to a problem, the answer was resonance, because often it was. If you don't know what resonance is, though, you're going to have a hard time getting those easy answers. So make sure that you do use this time, and try to use my office hours. Email me, use the Writing and Tutoring Center. Use any resource you can, because this topic is confusing, but we'll address it these next 2 days.